Good afternoon, everyone. My name is Janka Boborová and I'm going to talk about evaluation method for abduction algorithms. I collaborated with Martin Homola, who is my supervisor, and also with Jakub Kloc and Julia Pukancová. So let's start with introducing abduction. Abduction is an inference type similar to deduction and induction. But while induction provides new rules and deduction provides consequences, abduction provides new knowledge in the form of facts. So the basic task of abduction is to explain an observation while using some background knowledge. Some use cases of abduction can be seen on this slide. So, for example, medical diagnosis, criminology, or model-based diagnosis. Let me show you a simple example of abduction. So, we observe that John has a toothache. We also have some kind of knowledge base which consists of toothache causes. So, for example, a dental trauma causes toothache, then cavity causes sensitive teeth, and drinking cold drinks while having sensitive teeth also causes toothache. Then we ask why John does have toothache. We want to know this. And a possible explanation can be that John has dental trauma. Okay, but to work and reason over knowledge, we first need to formalize it. For this, we use description logics, and they are basically a family of formal languages that were designed to represent knowledge. They are mostly decidable and they are a formal foundation for widely used ontologies like OWL, for example. DL knowledge base consists of two components, D-box, which contains general knowledge, and then the A-box, which contains some knowledge about individuals. So again, it will be better with an example. We take those statements from the previous example, and toothache causes are basically our general knowledge, and then the fact that John has a toothache is some kind of knowledge about individual. When we want to formalize it, we should introduce vocabulary. So we have a set of individuals that contains only John, and then we introduce some atomic concepts like dental trauma, sensitive teeth, cavity, drank cold drink, and toothache. And with this, we can translate a statement one by one. So a dental trauma causes toothache will be translated into this. Then cavity causes sensitive teeth will turn to this, and similar with the last statement that drinking cold drink while having sensitive teeth causes toothache, and then the last statement will be translated into this. So John has a toothache. Now when we introduced description logic, we can finally introduce a formal definition for A-box abduction in DL. So given abducibles, which is some kind of set of A-box axioms, a DL knowledge base K, and an observation, which is also an A-box axiom, A-box abduction finds explanations E, which are subsets of abducibles, and they united with our DL knowledge base K entails the observation. So let's return to our example, and now we can actually formalize it. So we went through all statements before. But we can also formalize the question and the answer for that problem. So we are searching for some set of A-box axioms that united with K entails the observation that John has a toothache. And indeed, it is, for example, an axiom, dental trauma John. So John has a dental trauma, and it explains why he has a toothache. Well, there are multiple algorithms that can be used to compute explanations. We are focused on those with certain properties. So an algorithm should be complete. That basically means that it should guarantee to find all explanations. It should employ black box reasoning. So that means that to compute this explanation, it should only use some simple or basic reasoning tasks. So we can use some DL reasoner for it. And it also should be able to work for any logic. And we have researched and implemented these three algorithms that have the required properties. So minimal hitting set algorithm, hitting set 3 algorithm, and RC3 algorithm. Each of these algorithms can be also combined with merge explain method or algorithm to make it more interesting or effective, as we will see later. So in the end, we basically have 6 algorithms. So now I will go through the basic principle of these algorithms, but it will be very brief just to catch what they kind of do. So we know what is our task. We want to search for E such that K together with E entails observation O. Well, this task can be actually reduced to consistency checking. So instead, we will search for E's such that the union of K, E, and a complement of our observation is inconsistent. And with this idea, each of algorithms uses HS3, which is some kind of structure that systematically search through the space of all explanations, which in our case is basically abducibles, this space. And they try to search the explanation based on that reduction idea. So if I have to summarize it, in each node of these three, we are doing a consistency check of the union of K, negated observation O, and a path from the root of the tree to that certain node. And on the edges, we have some elements from the abducibles. So, for example, when we take this path and we do the consistency check of the mentioned sets, we get that it is inconsistent. So in this point, we know that A is our explanation. When we find that the set is consistent, we just continue with the search and create more children and continue with building the tree. And there are also some cases when we know we can prune the branch. It depends on a certain algorithm that we choose. So I'm not going to go into the details there. And basically, hybrids version are mostly the same, but instead of consistency checking, they call merge explain method, which basically consists of multiple consistency checking. But it should allow the algorithm to find explanation faster and also to prune the tree more effectively. So here are some examples of HS3. that were created solving our problem with John's toothache. So for John's toothache, when we take dimension algorithms, we basically get these trees. And we can see that even in this small example, the trees are pretty different in sizes and number of nodes. But interestingly, hybrid algorithms have the same tree, which is purely a coincidence. So it could not happen sometimes. It cannot happen sometimes. But because this example is so small, it happened that the tree is the same. Well, the smaller the tree, the better, of course. So the hybrid versions are probably the winner in this case. Well, all the algorithms are implemented in an experimental epoch abduction solver that is implemented in Java, and it employs black box approach, so we can use some external DL reasoner to deal with some small reasoning tasks, as we saw at the previous slides, mostly consistency checking. So it has some advantages, but I will not go through that right now. So here is an example of input file for that solver. It consists of an ontology, which represents our knowledge base, then an observation. It also needs to specify what algorithm to use to compute explanations. And the last bar here are abducibles. So when we can, it is always good to introduce abducibles to reduce search space as much as possible. So in this case, we kind of assume that John does not have sensitive teeth, so we just did not include it in abducibles. And now for our current goal, we want to evaluate these algorithms and compare them. So of course we want to find their strengths and weaknesses, and ideally some overall best algorithm. But what do we need to conduct an evaluation? Well, we do need some kind of implementation that has these algorithms, and we also need some test data set. Well, we have solver, that is nice, but what about test data set? Well, here comes an issue. There is no benchmark for this kind of problem, and also in papers the dataset details are usually not mentioned, so that is quite unfortunate. Here are some previous approaches, and I will briefly talk about them and point out some issues with them. So the first approach by Koopman uses 202 ontologies from a reasoning competition, and observations are generated in such a way that they were directly took from the ontology. And for abducibles, they were generated from 50 to 60% of vocabulary from the given ontology. The second approach only uses one ontology and generates observation in such a way that it introduces new individual A and then randomly chooses some concepts from that ontology which should be used in the which that individual should be included in, basically. And then for abducibles, they are set as only atomic A-box axioms or atomic A-box axioms and their complements. So now for the issues. When we directly take an observation from the ontology, there is high chance that it will have no explanations. So that can be an issue. Then for our algorithms, 50 to 60% of vocabulary is just too much. It is just not manageable when we have larger ontologies. And for the second approach, one ontology is too little. It should be more diverse, so we should have more ontologies in our data set. And generating observation like this is seen like too artificial because the concepts are chosen randomly. So in the end, the observation may not even make sense. So with this in mind, we have some requirements for our own dataset. It should have multiple diverse real-world ontologies. The observations should be interesting. That means that we should have some explanations for them, and they should not be artificial. We do not want artificial observations. And of course, we want to choose abducibles in a reasonable way. So let's start with knowledge base. We were inspired by the first approach by Koopman. So we chose that competition corpus, which included 1,920 ontologies. But that is a lot. So we applied some filtering criteria to choose only interesting ones. So those ontologies should be consistent. Their consistency check should take max 30 seconds, and they should have at least one individual, and loading time of the ontology should be less than 10 minutes. So ontologies that met these criteria were around 80-65, and here is some table which summarize their properties. As we can see, they really vary in the count of axioms and individuals. And when it comes to consistency check, the minimal is less than a second, and max is barely making it under 29 seconds. But interesting thing is average, which basically says that the majority of those ontologies take a little time. Okay, so now for the observation. Well, as I said, that we do not really want to take axioms directly from the ontology, but what about using entailments? I will show it on the example. So we have our ontology with 2 take causes, but we add this new axiom that says that Alice has dental trauma. Now we compute entailments, which basically is this one entailment that Alice has toothache, and this becomes our observation candidate. But when we try to search for explanations, right now we get no explanation because toothache Alice is already entailed. We designed it like that. But we can simply modify K and create K1 so that the observation is not entailed by this modified ontology. And we create it in a way that we simply delete this axiom that Alice has dental trauma. And now we can compute explanations. So as we can see, there are multiple explanations, and one of them is that one axiom that we deleted, which makes sense because we designed it in that way. So for a general process, we are given an ontology K, and we compute all entailments, which represents our new observations. Then for each entailment, we find its justifications, which is basically a formal term for sets that cause the entailment to be entailed. So that's just a formal term. And then we create a new ontology by deleting a box part of that justifications. So as we saw at in the example before, we deleted a box axiom. Okay, and in this way we can, in theory, generate observation that has at least one explanation. And for the last part, abducibles, well, we already know that random selection can lead to no explanations, so we have to do it in a meaningful way. Some better approach should be used. And we have two key elements that we can use in this case. So ontology modules, which enable us to get some kind of assertions which are connected to our observation. And then we can also use our justifications that we computed for the observation, because they should include things that should definitely be in those abducibles. So those are two important things. But this is still a work in progress because there are some issues with abducible size. And we should still some kind of manage how big we can be with them. Because even when we use modules, we can get a large amount of abducibles, and it is not manageable in some cases. So we should some kind of find a good solution for that. Okay, and now for the outlook. So in the near future, we will hopefully finish the dataset. Then we carry out the evaluation and, of course, analyze its results. And then there is a distant future which is not so clear, but there are some options. So we will see what path we will take. But basically, we can optimize the algorithms or explore some new types of those algorithms. Or we can also focus on a single use case and solve a specific problem with abduction. So that is all from me. Thank you very much.